In the year 2029, a rock the size of 3 football fields will fly closer to Earth than our own satellites. Its name is Apophis, after the ancient god of chaos and destruction. For years, scientists believed it might hit us. Now they know it will not. But something stranger is happening. As Apophis swings past, Earth's own gravity will grab it, twist it, and shake it. Its spin could flip. Boulders could break loose from its surface. Its entire orbit could bend in ways no one can fully predict. We will watch a solar system relic change shape in real time, live above our heads. No telescope required, just your eyes and a clear sky over Europe, Africa, or Asia. If this kind of story pulls you in, stick around and hit subscribe because we are only getting started. From a chaos god's return, to a rock that tumbles instead of spins, to forces powerful enough to reshape stone. Prepare yourselves. We begin. A telescope in Arizona catches a faint dot moving against the stars. It is June 2004. Nobody in the room knows it yet, but they just found something that will terrify astronomers for the next 2 years. The dot gets a name a few months later. Apophis, named after an ancient Egyptian god who lived in darkness and tried to destroy the sun every single night. The name feels dramatic. It feels like a joke. Then the math comes back and it stops feeling like a joke at all. Astronomers plot the orbit of this new object. It crosses Earth's path. Not close, not distant. Close enough that a small mistake in the calculations could mean the difference between a flyby and a disaster. The rock is roughly 375 meters wide. Picture the Empire State Building tipped on its side, drifting through space at 18 times the speed of a rifle bullet. That is Apophis. That is the object now heading toward a possible date with our planet. By December of that year, new data comes in. The odds of impact climb 2.7%. That number sounds small until you realize what it means for a planet of 8 billion people. Scientists use a tool called the Torino scale to rate asteroid danger, running from 0 to 10. Apophis hits level 4. No object in recorded history had ever reached that level with real, working odds behind it. Level 4 means, in plain words, a close encounter meriting attention by astronomers. It means pay attention because this one could be real. Newsrooms pick up the story. Headlines call it a doomsday rock. Some scientists worry about panic. Others worry about staying quiet and getting caught off guard. Meanwhile, the orbit of Apophis is still fuzzy, still full of uncertainty, like a photograph that has not finished developing. Every new telescope pointed at the sky either shrinks that fear or feeds it. Then something unexpected happens. Astronomers dig through old archives and find pictures of Apophis taken before anyone knew to look for it. Forgotten photographs, sitting in a database, holding the missing puzzle piece. These older images stretch the asteroid's tracked path across more time. More time means more precision, and precision is exactly what a fear like this needs. With the extended path in hand, scientists recalculate everything. The 2029 impact scenario disappears completely. Relief spreads through the community, but relief is not the end of the story. Buried inside the newer, more accurate models is a strange detail nobody expected. Apophis will still come close, closer than almost anything humanity has ever tracked, and when it does, the encounter will not leave the asteroid the way it found it. Because passing near a planet is not like passing through empty space. A planet has gravity. Powerful, invisible, patient gravity, capable of reaching across tens of thousands of kilometers and grabbing hold of a spinning rock. Apophis is heading directly into that grip. What happens when a chaos god meets the one force in the solar system it cannot resist? That question is where this story truly begins. Fear can hide in a number for years before anyone manages to kill it. For Apophis, that number was 2.7%. Small on paper, massive in consequence. Every percentage point represented thousands of simulated futures where a city, a coastline, or a nation faced a very bad day. Scientists needed one thing to finally silence that number: more data. Radar became the tool that changed everything. Unlike a normal telescope, which only catches reflected sunlight, radar facilities can bounce their own signal directly off an asteroid's surface. 2 giant dishes led the effort. One in the deserts of California, called Goldstone. One tucked into the hills of West Virginia, called Green Bank. Together they aimed their signals at Apophis while it sat millions of miles away and waited for the echo to return. That echo told scientists something incredible. Not just where Apophis was, but exactly how fast, exactly which direction, and exactly how its path curved through space. The measurement came back accurate to within about 150 meters at a distance of over 17 million kilometers. Imagine hitting a coin from across an entire country and knowing exactly where the coin landed. That is the kind of precision radar delivered. With this new information locked in, scientists ran the numbers one final time. The result changed everything. Every possible impact path for the next century vanished. Not shrank, vanished. 2029, gone. 2036, gone. Even the lingering worry about 2068 finally dropped away. Apophis, the chaos god, was no longer a threat to Earth. Not for 100 years. News outlets moved on almost overnight. The doomsday story ended, and doomsday stories do not stay in headlines once the doom disappears. But for scientists who had spent 2 decades tracking this rock, the story was only getting started. Because erasing the risk of a collision does something interesting. It clears the fear out of the way and lets a much stranger question come into focus. If Apophis will not hit Earth, what exactly will happen when it passes so impossibly close? Because close does not mean harmless once you consider gravity. A flyby at this distance is not a quiet, uneventful pass in the dark. It puts Apophis directly inside a zone where Earth's pull becomes strong enough to bend, twist, and reshape the asteroid itself. The danger of impact disappeared. The physics of the encounter did not. Researchers began building models. Not models asking will it hit us, but models asking what will it look like when it survives us. Spin rates, surface material, internal structure, all of it suddenly mattered in a completely new way. The story of Apophis shifted from a question of safety to a question of transformation. A rock is about to meet a planet up close and walk away changed. What changes, and how much, depends on forces most people have never had to think about. Forces that are about to take center stage. Picture every satellite that beams a weather forecast, a phone call, or a live sports broadcast down to your television. Most of the biggest ones sit in a specific ring around Earth, called geostationary orbit, roughly 36,000 kilometers up. It is a crowded, carefully managed neighborhood in space. On April 13th, 2029, an asteroid the size of a skyscraper is going to cut directly through that neighborhood. Apophis will pass at an altitude of about 32,000 kilometers. That number sits closer to Earth than the very satellites keeping our modern world connected. It sits at just 5.9 Earth radii from the center of our planet. For comparison, the Moon orbits at over 20 times that distance. Apophis will fly roughly 12 times closer to us than the Moon ever gets. This kind of close call with a rock this large does not happen often. Researchers estimate an object of this size passing this near to Earth occurs, on average, once every 7,500 years. Widen the search to anything this big or bigger, and the number stretches to roughly once every 800 years. In other words, nobody alive on Earth has ever witnessed anything like this before. Nobody in recorded human history has either. Despite slipping inside the satellite ring, engineers are not worried about a collision with anything mechanical up there. Geostationary satellites orbit in a narrow band directly above the equator. Apophis approaches from a different angle entirely, crossing that plane at a different point in space and time. The paths simply do not cross. Still, the comparison sticks in the mind for a reason. This is not some distant asteroid grazing the edge of the solar system. This is a rock threading itself through the same altitude as our communication infrastructure. Speed adds another layer to the spectacle. Apophis will be moving at roughly 27,000 kilometers per hour relative to Earth. At that pace, the asteroid could cross the entire continental United States in about 10 minutes. It arrives, sweeps past and departs, all within a matter of hours. The closest point of the entire pass happens in a blink, astronomically speaking. Then Apophis is already curving back out into deep space. For most of history, asteroid flybys have been invisible events, tracked quietly through telescopes while ordinary people never noticed a thing happened at all. This one breaks that pattern completely. Estimates suggest up to 7 billion people could have a chance to see Apophis crossing the night sky with nothing more than their own eyes. No telescope, no equipment, just a clear sky and the right hemisphere. But visibility is only the surface of the story. What makes this flyby remarkable is not simply how close Apophis gets, or how many people might glance up and see it drifting by. It is what happens to the asteroid itself the moment it enters Earth's gravitational grip. A silent, invisible tug of war is about to begin between a planet and a chaos god, and the god does not get to walk away unchanged. Most cosmic events unfold across years, centuries, or entire geologic ages. The Apophis flyby compresses all of its drama into roughly 7 hours. That single afternoon and evening becomes one of the most closely watched windows in the history of planetary science, packed with radar sweeps, telescope observations, and a level of public attention few asteroids ever receive. The ground track, the invisible line traced across Earth's surface directly beneath the asteroid's path, begins over the middle of the Atlantic Ocean. From there, it sweeps eastward, passing over parts of Africa and into Western Asia. At the moment of closest approach, expected around 9:45 in the evening Universal Time, Apophis will sit almost directly above the Atlantic, just west of Europe and Africa. Observers scattered across different countries will not all see the same thing at the same moment. Because Apophis passes so close to Earth, an effect called parallax comes into play. Two people standing in different countries, looking up at the same instant, will actually see Apophis positioned against different background stars. It is the same principle as holding a finger in front of your face and watching it shift when you close one eye, then the other, just scaled up to a planetary level. For skywatchers lucky enough to catch it, Apophis will not look like a fireball or a streak or anything from a disaster movie. It will resemble a single, steady point of light, gliding smoothly across the darkness, brighter and faster moving than typical stars or satellites. Peak brightness should make it visible to the naked eye across much of Australia, southern Asia, southern Europe and Africa, assuming clear skies and low light pollution. While casual observers watch a moving dot, professional instruments will be working far harder. Ground-based radar facilities plan to track the asteroid in real time throughout the entire encounter, refining our knowledge of its exact shape, spin, and structure down to fine detail. Telescopes around the world will point in the same direction simultaneously, creating one of the most thoroughly documented natural events ever recorded. And Apophis will not travel alone. At least one dedicated spacecraft, part of a mission called OSIRIS-APEX, will already be waiting nearby as the flyby happens, riding alongside the asteroid to capture data no ground-based instrument could ever gather. Having a spacecraft present during the exact moment Earth's gravity reshapes an asteroid is something that has never happened before in human history. All of this attention exists for one very specific reason. Scientists are not just watching Apophis pass by. They are watching to see how the encounter changes it. Every angle, every second, every instrument matters, because a transformation is coming. Somewhere in those 7 hours, deep inside a rock that has drifted quietly through space for billions of years, forces stronger than anything it has faced before are about to take hold, and nobody knows exactly what they will leave behind. Most objects in space spin the way a football spins when thrown with a perfect tight spiral. Smooth, predictable, one clean axis turning at a steady rate. Apophis breaks that pattern entirely. Instead of spinning cleanly, it tumbles, wobbling through space like a football thrown badly, end over end, off balance, never settling into a rhythm. Scientists call this a non-principal axis rotation state. In simpler terms, Apophis is not spinning around its shortest, most stable axis, the way a well-thrown object naturally would. Its rotational momentum instead wobbles at an average angle of about 37 degrees away from that stable axis. Picture spinning a can of soup versus spinning a badly packed suitcase. The can spins true. The suitcase wobbles, twists, and fights against your hand the entire time. This tumbling motion makes Apophis unusually difficult to study. A normal, steadily spinning asteroid gives astronomers a predictable pattern of light as it rotates, brightening and dimming on a reliable schedule. Apophis refuses to cooperate. Its light curve shifts unpredictably, shaped by a rotation that never quite repeats the same way twice. For years, this tumbling behavior remained one of the asteroid's strangest and least understood traits. Right now, one full tumble of Apophis takes roughly 30 hours to complete. That is longer than an entire day and night cycle here on Earth. A slow, lumbering wobble, drifting through the vacuum of space largely undisturbed because nothing has come close enough to interrupt it in a very long time. That is about to change. As Apophis approaches Earth in 2029, it will pass close enough for our planet's gravity to reach directly into that tumbling motion and grab hold of it. Earth is roughly 81 times more massive than the Moon, and thousands of times more massive than Apophis itself. When an object that size gets close enough, its gravitational pull does not simply nudge a smaller body, it reaches inside and rearranges it. Researchers running detailed simulations have found that Apophis's 30-hour tumble could shift dramatically during the encounter, potentially slowing down or speeding up to somewhere between 10 and 15 hours. Both outcomes have appeared in different models. Some simulations show the tumble accelerating, others show it decelerating. The direction of the change depends on tiny, hard-to-measure details about the asteroid's internal mass distribution, details scientists still do not fully know. That uncertainty is not a failure of the research. It is the entire point of watching this event unfold live. Nobody has ever measured, in real time, exactly how a planet's gravity reaches into a tumbling asteroid and changes its motion. Apophis is about to become the first confirmed case study, a natural experiment billions of years in the making, arriving right on our doorstep. Before the encounter, its wobble had nowhere left to escape. Stand at the edge of a swimming pool and drag your hand slowly through the water. The water nearest your hand moves fast. The water farther away barely moves at all. That difference in pull, strong up close, weak at a distance, is the exact same principle behind one of the strangest forces about to act on Apophis. Scientists call it a tidal force, and it is powerful enough to twist solid rock. Here is how it works. Earth's gravity does not pull on every part of Apophis with equal strength. The side of the asteroid facing Earth during closest approach feels a noticeably stronger pull than the side facing away. That mismatch creates a stretching effect, like someone gently pulling on both ends of a piece of dough. The asteroid does not just get tugged toward Earth, it gets stretched ever so slightly along the line connecting the two bodies. This same tidal stretching is the reason our oceans rise and fall every single day, pulled by the Moon's uneven gravity across Earth's surface. The Moon is far smaller than Earth, yet it still manages to lift the entire ocean by measurable amounts, twice a day, every day for billions of years. Now imagine that same stretching effect, except instead of acting on a liquid ocean, it acts directly on the loose rubble-covered surface of a spinning asteroid. Apophis is not a solid single chunk of stone. Many scientists believe it is closer to a rubble pile, a loosely bound collection of rocks and dust held together mostly by its own weak gravity rather than any strong internal structure. That distinction matters enormously here. A solid rock might resist tidal stretching with barely a shudder. A rubble pile has far less to hold it together. During the 2029 flyby, Apophis will pass at a distance of just under 6 Earth radii, close enough that these tidal forces become strong enough to matter, but importantly still outside what scientists call the Roche limit, the distance at which tidal forces become powerful enough to tear a loosely bound object apart completely. Apophis will not be ripped apart, it will simply be shaken. Shaken is still a dramatic word for what is about to happen to a rock that has drifted peacefully through space for billions of years. Researchers studying the encounter describe potential effects including surface refreshing, small-scale structural changes, and vibrations rippling through the asteroid's loose material. In plain terms, the surface of Apophis may shift, crack, and resettle itself during the hours surrounding closest approach. None of this happens through any physical contact. Earth and Apophis never touch. The entire transformation occurs purely through the invisible reach of gravity, stretching across tens of thousands of kilometers of empty space. A planet is about to reshape a piece of the early solar system without laying a single finger on it, and the only proof will be the marks left behind on the asteroid's surface once the encounter finally ends. Somewhere on the surface of Apophis sits a boulder that has not moved in millions of years. It rests in near total stillness, held in place by gravity so weak that a person standing on the asteroid could likely jump clean off its surface and drift away. That boulder is about to experience the most violent moment of its entire existence, and it will not need an explosion or an impact to make it happen. Scientists studying the flyby have identified specific danger zones scattered across the asteroid's surface, regions they describe as sitting under significant stress even before Earth's gravity gets involved. These areas already exist close to the point of shifting on their own, balanced precariously between staying put and giving way. Tidal forces during the flyby do not need to create new instability. They only need to nudge material that is already teetering on the edge. Researchers running detailed models describe the likely result as a kind of resurfacing event. Loose material, ranging from fine dust to sizable boulders, could shift position, slide down slopes, or become dislodged entirely as Earth's gravity stretches and vibrates the asteroid's structure. On a body with almost no gravity of its own, even a small nudge can send material tumbling in slow motion, drifting instead of crashing, the way a feather might fall on the moon. Picture a landslide happening in near silence, stretched out over minutes instead of seconds. Boulders the size of cars sliding gently across a landscape untouched since before humans existed. No explosion, no sound wave, since there is no atmosphere to carry one, just quiet, gradual motion, triggered entirely by an invisible gravitational hand reaching across tens of thousands of kilometers of space. This matters far beyond simple spectacle. Every boulder that shifts, every patch of dust that settles into a new position, changes the physical map of Apophis permanently. Scientists studying the asteroid before and after the flyby will essentially be comparing two different versions of the same object, one frozen in its ancient, undisturbed state, and one freshly reshaped by its brush with Earth. That comparison offers something incredibly rare in planetary science. Normally, studying how an asteroid's surface evolves over time requires waiting millions of years, or sending an expensive spacecraft mission to physically visit and monitor the object directly. Apophis is offering to demonstrate the evolution in a single afternoon, live, while telescopes and spacecraft watch every second of it unfold. Spacecraft already positioned near the asteroid, including the mission known as OSIRIS-APEX, aim to capture this transformation directly, gathering before and after imagery that could reveal exactly which regions shifted and by how much. For the very first time, scientists may get to watch an asteroid's surface rearrange itself in real time. Driven purely by gravity, with no collision, no explosion, and no warning beyond the math that predicted it years in advance. Gravity is not the only force capable of steering an asteroid. Sunlight can do it too, given enough time. It sounds impossible at first. Light has no mass, and yet, across millions of years, it manages to nudge entire asteroids off their original paths. Scientists call this the Yarkovsky effect, and Apophis has become one of its most closely studied examples. The mechanism starts simply enough. As Apophis rotates, one side faces the sun and absorbs heat, while the opposite side faces away and slowly cools. A short while later, as the asteroid continues spinning, that heated side begins releasing its stored warmth back out into space as infrared radiation. Here is the strange part. Radiation carries a tiny amount of force with it when it leaves a surface, similar to the way exhaust pushes a rocket forward. Because Apophis is not radiating heat evenly in every direction at every moment, this creates a small, continuous, one-directional push. It is an incredibly weak force, far too small to feel or even measure directly on any short time scale. But asteroids do not experience the solar system across a single afternoon. They experience it across millions of years, and even a whisper of a push, repeated relentlessly across that much time, adds up into something significant. Consider a real-world example. A different asteroid, similar in size to Apophis, wandered off its expected path by roughly 160 kilometers over just 12 years, purely from this heat-driven push. That kind of drift may sound small compared to the vastness of space, but for scientists trying to calculate exactly where an asteroid will be decades or centuries into the future, 160 kilometers is an enormous meaningful gap. For Apophis specifically, researchers currently estimate the Yarkovsky effect shifts its orbit by roughly 200 meters per year, a slow but steady drift measured through years of careful tracking. That number might sound tiny, but remember, this is the same subtle force that once complicated the entire 2068 impact question, forcing scientists to run new calculations just to rule out a collision that the original numbers alone could not fully eliminate. Here lies the deepest irony of the entire Apophis story. A rock large enough to threaten a city can still be steered, ever so slightly, by nothing more than warmth leaving its own surface. Sunlight itself becomes an invisible hand, resting gently on the asteroid for millions of years, patiently altering its future 1 meter at a time, and this quiet, ongoing push is about to collide with a much stronger, much faster force. As Apophis tumbles through its 2029 encounter with Earth, its rotation, its shape exposure to the Sun, and its surface temperature patterns could all shift dramatically. Change any of those factors, and the Yarkovsky effect itself changes too. A slow force is about to be rewritten by a fast one, and nobody knows exactly what the new push will look like afterward. Two forces are about to collide inside a single afternoon. One force has worked on Apophis patiently for millions of years, the slow thermal push of sunlight reshaping its orbit meter by meter. The other force needs only a few hours to act, arriving suddenly and departing just as fast, powerful enough to rewrite decisions that took the Sun ages to make. That second force is Earth's gravity, and during the 2029 flyby, it plans to rewrite Apophis's rotation almost entirely. Scientists modelling the encounter describe changes to the asteroid's spin state that would normally take an object like this thousands, even millions of years to develop naturally. Apophis is about to experience that same magnitude of change compressed into a single, dramatic afternoon. The asteroid's spin axis itself, the invisible line it rotates around, is expected to shift by 10 degrees or more during the encounter. It will also move closer toward alignment with the flat plane of its orbit around the Sun. 10 degrees might sound small, but for an object that has held roughly the same orientation for millions of years, drifting silently and predictably through space, that shift represents a genuinely violent disruption to its stability. Layered on top of that shift sits the rotation speed itself. Remember, Apophis currently tumbles through one full rotation roughly every 30 hours. Detailed models suggest that number could plunge to somewhere between 10 and 15 hours following the flyby, nearly cutting its rotation period in half, or possibly even further. Other simulations point the opposite direction entirely, suggesting the tumble could slow down instead of speeding up. This uncertainty is not a gap in the science. It reflects something scientists still cannot fully measure from Earth: the precise internal structure of Apophis itself. Is the asteroid denser toward its centre, or more evenly spread throughout its body? Are there hidden voids, pockets, or clusters of denser material buried beneath the surface? Every one of those hidden details influences which direction the spin will shift, and by how much. That is precisely why scientists consider this flyby such a rare scientific gift. The direction and magnitude of the spin change will essentially reveal information about Apophis's interior that no telescope has ever been able to measure directly. Watching how the asteroid responds to Earth's gravity becomes a way of looking inside it, the same way a doctor might learn about bone density by studying how a body responds to physical stress. Once the encounter ends and Apophis pulls away from Earth, it will carry this new spin state with it, unchanged, for potentially thousands of years into the future. The tumbling motion that took millions of years to settle into its current rhythm is about to be reset in a single evening. And that new rhythm will decide, in turn, exactly how the slow, patient push of sunlight continues shaping this asteroid's path for every year that follows. Every asteroid carries a kind of memory inside it, written not in words but in structure, density, and shape. Apophis has drifted through the solar system for billions of years without ever colliding with a planet, without ever being melted down by intense heat, without ever undergoing the kind of transformation that reshapes most large objects over time. In many ways, it survives today as a nearly untouched fossil from the earliest era of our solar system. That word, fossil, is not used loosely here. Scientists studying rubble pile asteroids like Apophis believe objects like this preserve original material left over from the earliest days of planet formation, roughly 4.5 billion years ago. While Earth melted, cooled, formed layers, and constantly reshaped its surface through volcanoes and weather, Apophis simply drifted, largely unchanged, a frozen snapshot of conditions from the solar system's earliest chapter. This is exactly what makes the 2029 flyby such a rare scientific opportunity. Under normal circumstances, studying the interior of an asteroid requires sending an expensive spacecraft on a multi-year journey, then attempting a risky landing or sample collection mission. Apophis is instead bringing itself directly to us, flying close enough that Earth's own gravity does the work of probing its interior, all without a single spacecraft needing to touch its surface. As Earth's gravity stretches, twists, and reshapes Apophis during the encounter, the exact way it responds becomes a kind of diagnostic test. A rock with a dense, evenly distributed interior will respond differently than one filled with hidden gaps, loose material, or unevenly clustered mass. By carefully measuring the spin changes, the surface shifts, and the drift in its orbit following the flyby, scientists can work backward, piecing together clues about what lies hidden beneath Apophis's surface. This is precisely why a dedicated spacecraft mission exists to accompany the encounter. Known as Osiris Apex, it represents a repurposed version of an earlier mission that had already successfully collected samples from a different asteroid years before. Rather than retire the spacecraft after its first job was complete, scientists redirected it toward Apophis, positioning it to arrive and observe the flyby directly, capturing data no ground-based telescope could ever hope to gather. Combining spacecraft observations with ground-based radar and telescope tracking creates something remarkable, a complete before and after record of an ancient object's transformation. Scientists will know precisely how Apophis looked and moved before the encounter, and precisely how it looks and moves afterward. Few objects in the history of astronomy have ever been documented this thoroughly, across a single brief window of time. What emerges from all this data extends far beyond simple curiosity about one asteroid. Apophis becomes a natural laboratory for testing our understanding of how rubble pile objects behave, how tidal forces interact with loosely bound material, and how planets quietly reshape the smaller bodies that wander too close. Every answer extracted from this ancient fossil helps prepare scientists for the next asteroid, one that might not announce its arrival with 25 years of advance warning. A single evening in 2029 will decide how Apophis moves for centuries afterward. That claim might sound exaggerated, but the physics behind it is entirely real. Before the flyby, scientists estimate the Yarkovsky effect pushes Apophis's orbit outward by roughly 200 meters per year, a slow, steady drift shaped by heat radiating unevenly off its surface. After the flyby, that number could look completely different. Detailed models exploring this exact question have produced a striking range of outcomes. Some simulations suggest the drift rate could decrease to around 160 meters per year following the encounter. Others suggest it could climb dramatically higher, potentially reaching as much as 300 meters per year. That represents nearly a doubling in speed or a meaningful slowdown, depending entirely on details scientists still cannot fully predict in advance. Why does a single flyby carry so much power over a force that normally moves at a glacial, patient pace? The answer connects directly back to everything discussed so far. Remember, the Yarkovsky effect depends heavily on an asteroid's spin rate, its spin axis orientation, and how sunlight strikes its surface throughout each rotation. Change any of those three factors, and the entire thermal push recalculates itself from scratch. The 2029 encounter is expected to change all three factors simultaneously. Apophis's rotation period could shift dramatically. Its spin axis could tilt by 10 degrees or more. Its surface itself may shift and resettle, as loose material relocates during the tidal stretching. Layer all of these changes together, and the asteroid essentially receives a brand new thermal fingerprint, one that determines how sunlight will nudge its orbit. For potentially thousands of years into the future, this matters enormously for long-term forecasting. Scientists studying potentially hazardous asteroids do not simply calculate where an object will be next year, or even next decade. They model orbital paths stretching centuries into the future, searching for any possibility of eventual close encounters or impacts. Every one of those distant future calculations depends on accurately understanding the Yarkovsky drift rate, and that rate is about to be rewritten in a matter of hours. Researchers openly acknowledge this uncertainty rather than hiding from it. Prior to the flyby, they can only offer a range of possible outcomes, not a single confident answer. That range itself becomes valuable information. A boundary scientist can test their models against once real observations come flooding in during and after the actual event. Every asteroid mission carries lessons for the next one, and Apophis is preparing to teach an entire generation of scientists about exactly this kind of unpredictable transformation. Once the encounter finally ends and Apophis drifts back out into deep space, its new orbit will begin quietly accumulating change again, meter by meter, year by year, exactly as before. Except this time, scientists will know, with far greater confidence, precisely how that drift behaves. The Chaos God does not just survive its brush with Earth. It leaves the encounter permanently altered, carrying an entirely new signature written by sunlight into its future path. Somewhere above Apophis, riding invisibly alongside it as it plunges toward its closest approach to Earth, a spacecraft will be watching everything unfold. Its name is Osiris Apex, and its presence during this exact moment represents something that has genuinely never happened before in the history of space exploration. No human-made object has ever accompanied an asteroid through an encounter this dramatic, this close, and this well documented. The spacecraft itself carries an unusual history. It began its career under a different name entirely, tasked with travelling to a completely different asteroid, collecting a physical sample of rock and dust, and successfully returning that sample safely to Earth. That original mission succeeded brilliantly. Rather than let a fully functional, still capable spacecraft simply drift into retirement afterward, mission planners made a bold decision: redirect it, send it toward Apophis instead, timing its arrival to coincide precisely with the historic 2029 flyby. Engineering a rendezvous with a tumbling, unpredictable target is far from simple. Researchers studying the mission have outlined several possible strategies for how the spacecraft might maintain a safe, useful position throughout the encounter. One option involves holding a distant, stable orbit around the asteroid. Another involves hovering directly along the invisible line connecting Earth and Apophis. A third involves attempting close orbital operations around the asteroid itself, tracking its movement in real time as Earth's gravity begins reshaping it. Each approach carries genuine risk. Apophis is not a calm, steadily spinning object. It tumbles unpredictably, and that unpredictability only worsens as Earth's gravity actively works to change its rotation during the flyby itself. A spacecraft attempting to maintain a stable position near an asteroid, whose spin rate might suddenly shift from 30 hours down to 10 faces, genuine navigational challenges that mission planners have spent years preparing for. Despite these difficulties, researchers studying the mission's feasibility have concluded that close proximity operations remain achievable, even challenging conditions considered. That conclusion matters enormously because a spacecraft stationed nearby offers something no ground-based telescope or radar dish possibly could: an up-close front-row view of the exact moment tidal forces begin reshaping the asteroid's surface. Ground-based instruments will contribute their own critical piece of this puzzle. Radar facilities plan to track Apophis continuously throughout the encounter, refining measurements of its shape, spin and structure in real time. Telescopes scattered across the globe will watch simultaneously, creating overlapping streams of data from multiple angles at once. Combined together, a spacecraft riding alongside the asteroid and instruments tracking it from across an entire planet, this event is shaping up to become one of the most thoroughly observed natural phenomena in scientific history. Every angle covered, every second recorded. All aimed at capturing something that took gravity mere hours to accomplish after nature spent over 4 billion years building the object being transformed. 25 years. That is roughly how much advance warning humanity received before Apophis makes its historic close approach. 2 decades and a half of tracking, calculating, refining and preparing, all building toward a single well-documented evening in 2029. That much lead time might sound generous, almost comfortable. It is not the standard. It is closer to a rare exception. Consider how differently things unfolded for a completely different asteroid in recent memory. In October of 2025, an object named 2025 TF streaked directly over Antarctica, passing just 428 kilometers above Earth's surface, an altitude similar to where the International Space Station orbits. Astronomers did not spot it coming. They discovered it several hours after it had already made its closest approach and departed. That asteroid posed no real danger, measuring only about 1 to 3 meters across, small enough to have simply burned up as a bright fireball had it entered the atmosphere. But the lesson embedded in that near miss carries weight far beyond its tiny size. If astronomers can miss an object passing this close, arriving from a direction that happened to align poorly with ground-based telescopes. What does that suggest about our ability to catch something larger, arriving from a similarly difficult angle? An even more extreme example arrived back in 2020, when an asteroid called 2020 QG passed just 2,950 kilometers above the southern Indian Ocean, setting the record at the time for the closest known non-impacting flyby ever recorded. That object was not detected in advance either. It was spotted roughly 6 hours after it had already swept past Earth, discovered only because it happened to be departing directly through a telescope's field of view. Apophis represents the complete opposite scenario. Decades of advanced tracking, precisely calculated arrival times, confirmed safety, a coordinated global effort involving telescopes, radar facilities, and a dedicated spacecraft, all working together in perfect synchronization. This level of preparation stands as a genuine triumph of planetary defense, proof that patient, careful science can transform a potential threat into a celebrated scientific event. But triumphs like this rely entirely on advanced detection, and advanced detection depends on telescopes actually spotting objects while they still sit far enough away to matter. Smaller asteroids similar in size to the two that snuck past undetected remain genuinely difficult to catch using current monitoring systems, particularly when they approach from certain angles relative to the Sun. Apophis earned its 25 years of warning, purely because it happened to be large enough and bright enough for early telescopes to catch in 2004. The next object heading our way might not offer that same courtesy. It could arrive from an unlucky angle, at a smaller size, sneaking past our current detection networks entirely, giving scientists mere hours to respond instead of decades. Apophis shows us what preparation looks like when it works. The near misses show us exactly what happens when it does not. Tracking an asteroid sounds like a simple task on the surface. Point a telescope at the sky, take a picture, repeat. The reality has grown considerably more complicated in recent years, and the culprit is not confusion about physics or a lack of good equipment. The culprit is traffic, and it is orbiting directly above our heads in ever-increasing numbers. Thousands of satellites now circle Earth, forming massive networks known as mega-constellations, delivering internet access and communication services to locations around the globe. These networks have expanded rapidly, and every additional satellite adds one more bright moving object crossing through the night sky. For most people, this goes unnoticed. For astronomers hunting for faint, fast-moving asteroids, it creates a genuine and growing problem. The most critical window for spotting near-Earth asteroids tends to occur during dusk and dawn, the brief periods when the sky darkens enough to reveal faint objects, while the sun still illuminates anything passing close to Earth from certain angles. This exact window happens to be when satellite trails become most visible and most disruptive, streaking directly across the same patches of sky astronomers depend on for detecting incoming threats. Imagine trying to spot a single specific firefly, blinking somewhere across a massive darkened field, while dozens of bright flashlights sweep back and forth across your view at the same time. Each individual light might not seem overwhelming on its own. Together, they make picking out the one faint, meaningful signal considerably harder than it used to be. This growing complication arrives at an inconvenient moment. Scientists already understand that some of the most dangerous asteroids, the small, difficult-to-detect kind capable of sneaking past current monitoring efforts entirely, tend to be spotted during these exact same critical hours. Adding more bright, moving obstacles into that narrow observing window does not simply create an inconvenience. It actively increases the odds that a genuinely dangerous object slips through unnoticed. None of this diminishes the remarkable achievement represented by Apophis itself. Decades of careful tracking successfully turned a genuine, credible threat into a fully understood, safely predicted scientific event. That success story remains real and worth celebrating, but it also arrived under observing conditions considerably cleaner than what astronomers face today. Before satellite mega-constellations multiplied into the thousands, scientists and policymakers continue working to address this challenge, exploring coordination efforts between satellite operators and observatories, alongside new detection technologies designed to filter out satellite interference more effectively. The race between building better asteroid detection systems and managing an increasingly crowded sky has become one of the quieter, less discussed challenges in modern planetary defense. Apophis gave humanity a generous 25 years of warning. Whether the next dangerous object receives anywhere close to that same courtesy may depend on how well we manage the sky we now share with our own machinery. Even after the 2029 and 2036 impact scenarios disappeared completely from the calculations, one final possibility lingered stubbornly in the background: 2068, a distant future date, decades beyond anyone currently reading this story's typical planning horizon, yet still close enough that scientists refuse to dismiss it without absolute certainty. The reason this particular date proves so difficult to eliminate traces directly back to everything already explored about the 2029 flyby. Because that close encounter with Earth will meaningfully alter Apophis's orbit, any calculation attempting to predict where the asteroid travels afterward depends entirely on knowing precisely how that alteration unfolds. Get the 2029 outcome slightly wrong, and every prediction stretching beyond it inherits that same uncertainty, magnified further with each passing year. The Apophis effect sat at the centre of this lingering problem. Remember, this slow, sunlight-driven push depends heavily on an asteroid's exact spin state, something the 2029 flyby is expected to change dramatically and unpredictably. Scientists working through these calculations years in advance essentially found themselves trying to predict the future path of an object whose fundamental physical behaviour had not yet been determined. Prior estimates placed the odds of an eventual 2068 collision at roughly 1 in 150,000, a genuinely small number, yet not quite small enough to ignore entirely given the stakes involved. When newer data revealed the added complexity of the Apophis effect, those older odds were effectively thrown into question, requiring fresh calculations built on more complete information. Additional observations gradually chipped away at this remaining uncertainty. Continued radar tracking combined with steadily improving models of Apophis's shape, structure, and thermal behaviour eventually allowed scientists to rule out the 2068 impact scenario as well. Today, current projections show no impact risk from Apophis for at least the next century, a conclusion built on genuinely comprehensive, thoroughly verified data. Notice the careful wording scientists continue to use here. Not next several centuries, not forever, at least the next century. That distinction matters, and it is not simple caution for its own sake. It reflects an honest, scientifically grounded acknowledgement that Apophis's future path beyond the 2029 flyby still depends on outcomes that have not happened yet, outcomes tied directly to exactly how Earth's gravity reshapes the asteroid's spin and surface during those critical 7 hours. This is precisely why the 2029 encounter carries scientific weight extending far beyond mere spectacle or curiosity. Every measurement gathered during that flyby, every detail learned about how Apophis responds to Earth's gravity, feeds directly into refining our understanding of where this ancient chaos god travels next. The distant future of Apophis is not written yet. It is being calculated in real time, one radar echo and one telescope observation at a time, racing to stay ahead of an object that has already surprised scientists more than once before. Space agencies typically spend billions of dollars and many years designing missions capable of studying how planets and asteroids interact. Building a spacecraft, launching it, guiding it across millions of kilometers, and positioning it perfectly near a target object represents one of the most expensive, complicated undertakings in modern science. Apophis is offering something remarkable in comparison. A fully formed natural laboratory arriving entirely on its own, requiring no expensive journey to reach it. Scientists studying planetary defense have long wanted answers to a specific set of questions. How exactly does a planet's gravity affect a smaller asteroid passing nearby? How does tidal stretching influence a rubble pile object's surface and internal structure? How predictable, or unpredictable, is the resulting change in spin, shape, and orbital path? Under normal circumstances, answering these questions convincingly would require either an extremely rare natural event or an enormously expensive engineered one. Apophis delivers the rare natural event directly to Earth's doorstep. without any spacecraft needing to travel anywhere at all. Researchers studying near-Earth asteroids describe encounters of this type and magnitude as occurring, on average, only once every several centuries. Waiting for the next comparable event through pure chance alone would mean waiting far longer than any single scientific career could span. This is precisely why so much coordinated effort has poured into observing this specific flyby as thoroughly as humanly possible. Every radar facility, every telescope, every spacecraft instrument pointed toward Apophis represents an attempt to extract maximum scientific value from an opportunity that will not repeat itself again anytime soon, and one that no other generation of scientists has ever had the chance to observe with anything close to today's technology. The knowledge gained here extends well beyond simple curiosity about one particular asteroid. Understanding precisely how tidal forces reshape a rubble pile object carries direct practical implications for planetary defense more broadly. If humanity ever needs to deflect a genuinely dangerous asteroid heading toward Earth, understanding exactly how these loosely bound objects respond to gravitational and physical stress becomes critically important information, not simply academic interest. Consider an earlier example already tested directly. A previous mission successfully altered the orbit of a small asteroid moon by deliberately crashing a spacecraft into it, demonstrating that humanity possesses genuine working technology capable of nudging a dangerous object off a collision course. Apophis offers a complementary lesson, revealing how a much larger gravitational encounter, rather than a direct impact, reshapes an object of this type and size. Every piece of data gathered during the 2029 flyby becomes a permanent addition to humanity's growing understanding of how to protect this planet from future threats. A chaos god, drifting quietly through space for over 4 billion years, is about to hand scientists a masterclass in planetary defense, delivered entirely for free, requiring nothing more than patience, preparation, and a sky full of instruments ready to watch closely when the moment finally arrives. Some numbers only become real once you attach them to something familiar. 375 meters. That measurement alone might slide past most people without leaving much impression. Compare it instead to the Empire State Building, a structure recognized by silhouette alone across the entire world, and suddenly the scale of Apophis becomes impossible to ignore. Tip that entire skyscraper onto its side, antenna, observation deck, 70 plus stories, all of it laid flat. That rough length, spire included, matches the approximate width of Apophis as it tumbles silently through space. Not a small pebble, not a modest boulder, a structure large enough to dominate a city skyline, drifting through the vacuum at speeds exceeding 27,000 kilometers per hour. Now picture that same skyscraper-sized object, still tumbling unpredictably, sliding directly through the same altitude band occupied by the satellites carrying television broadcasts, weather forecasts, and long-distance phone calls around the entire planet. That comparison alone captures something words like close approach or near miss often fail to fully convey. This is not a distant curiosity glimpsed faintly through a research telescope. This is a landmark-sized object passing directly through humanity's own technological backyard. Yet size represents only part of what makes this encounter remarkable. Remember everything already explored about Apophis's internal behavior, its tumbling rotation, its uncertain internal structure, its rubble pile composition held together by little more than its own weak gravity. A structure the size of the Empire State Building, but lacking the steel framework, the poured concrete foundations, or the engineered stability holding that real building together. Instead, held loosely, precariously, by forces barely strong enough to keep it from drifting apart entirely on its own. That fragility becomes precisely why the tidal forces discussed earlier carry so much scientific weight. A solid, single piece of rock this size might shrug off Earth's gravitational pull with minimal visible effect. A loosely bound rubble pile, stretched and shaken by that same gravitational pull, responds in ways scientists are still working to fully predict, potentially reshaping its surface and altering its spin in dramatic, visible ways. Consider one final scale comparison. Apophis will pass roughly 12 times closer to Earth than the Moon during this flyby, all while measuring roughly comparable in length to one of humanity's most recognizable skyscrapers. Few natural objects in recorded history have combined this particular blend of massive size and impossibly close proximity, arriving together in a single, well-documented event. This is the object now heading toward Earth's gravitational grip in 2029. Not a fragment, not a boulder. A structure large enough to anchor a skyline tumbling end over end through space, about to meet a planet powerful enough to reshape it in a matter of hours. Everything explored across these chapters, the spin changes, the surface shifts, the orbital drift, all of it is about to happen to something built on a scale the human mind can finally truly picture. Every model built to predict what happens to Apophis in 2029 relies on one critical number. Scientists still cannot pin down with confidence. Density. Not the density of the surface, which telescopes and radar can estimate reasonably well, but the density hidden deep inside the asteroid, buried beneath layers of rock and dust no instrument has ever directly touched. This missing number matters more than almost anything else in the entire story. Two asteroids could look completely identical from the outside, same size, same shape, same surface color, and still respond in completely different ways to Earth's gravity, purely because of how mass sits distributed inside them. One might carry a dense, compact core. Another might hide large pockets of empty space, sitting like air bubbles trapped inside a loaf of bread. Scientists studying Apophis describe it as intermediate between two different asteroid types, sitting somewhere between categories astronomers label S-type and Q-type, based on how sunlight reflects off different mineral compositions. That classification offers useful clues, but clues are not certainty. Without a spacecraft physically landing and drilling into the surface, a step nobody currently plans to attempt, the true internal structure remains locked behind educated guesswork. This uncertainty explains why competing models sometimes produce opposite predictions. Remember the rotation period, potentially dropping to 10 hours, or possibly stretching to 15. Remember the Yarkovsky drift rate, either falling toward 160 meters per year or climbing toward 300. These are not contradictions or mistakes. They represent genuinely different possible answers, each one valid under a different assumption about what sits hidden beneath the surface. Researchers have found a clever workaround for this problem, one that turns the flyby itself into the measuring instrument. Rather than needing to know the internal density in advance, scientists can instead observe precisely how Apophis actually responds during the encounter, then work backward to calculate what internal structure would explain that specific response. The flyby becomes a diagnostic scan, similar to how doctors infer bone density from how a body responds to certain physical tests, without ever needing to open it up directly. This single flyby carries the potential to resolve a scientific question that has remained genuinely unanswered since Apophis was first discovered over 2 decades ago. What exactly is this object made of, and how is that material arranged inside it? An answer that would normally require an expensive dedicated mission is instead arriving as a natural byproduct of an event already scheduled to happen regardless. Every instrument aimed at Apophis during those 7 critical hours will be watching for one thing above all else: clues buried inside the exact numbers describing how much the spin changed, how far the surface shifted, and how the orbit bent afterward. Somewhere inside that data sits the answer to a question that has quietly followed this chaos god since the moment it was first spotted, drifting through the darkness over 2 decades ago. Missions to study asteroids typically happen once. Spacecraft launch, travel for years, arrive, gather data, and that becomes the complete record available to scientists, sometimes for decades afterward. Apophis is quietly rewriting that expectation, because its 2029 flyby represents only the first of several close encounters this same object plans to make with Earth across the coming decades. Earlier calculations already confirmed that Apophis will not strike Earth during its next several documented approaches, stretching across at least the next century. But no impact does not mean no return visit. Orbital mechanics guarantee that an object crossing Earth's path this closely will continue crossing paths with our planet repeatedly, over and over across future decades, each time offering another opportunity for careful observation. This repeating pattern transforms Apophis from a single dramatic event into something closer to an ongoing research subject, one scientists can study, compare, and revisit across multiple encounters rather than just once. Imagine studying a single photograph of a hurricane versus tracking that same storm system across an entire week, watching precisely how it strengthens, weakens, and shifts direction over time. Multiple encounters offer exactly that kind of extended observational power. The 2029 flyby carries special importance specifically because it arrives first, and because it happens to occur at such an unusually close distance. Whatever spin changes, surface shifts, and orbital drift occur during this initial encounter will directly shape what scientists expect and specifically watch for during every subsequent approach that follows in later years. This creates something like a natural before and after again record, stretching across potentially decades of continuous observation. Scientists rarely receive this kind of repeated access to the same object under changing conditions. Most asteroids studied up close get one visit, one dataset, and then drift back into the vast emptiness of space, never to be studied this closely again. Apophis breaks that pattern entirely. Because its orbit keeps bringing it back toward Earth's neighbourhood, scientists effectively gain a long-term research subject, one whose behaviour they can track, evolving in real time across multiple close approaches. Each encounter offers a chance to verify whether earlier predictions held true, and to refine models further based on what actually happened, rather than what models alone predicted in advance. This long-term relationship between Apophis and Earth represents something genuinely unprecedented in the history of asteroid science. A single object, tracked continuously across decades, revealing not just a single snapshot of how gravity reshapes a rubble pile asteroid, but an entire evolving story, unfolding one close approach at a time. The Chaos God is not simply visiting once and disappearing, it is settling into a long, repeating relationship with the very planet it once threatened to strike. Every ambitious space mission begins with careful planning, dedicated funding, and years of preparation before launch. The spacecraft now positioned to observe Apophis during its historic flyby very nearly never happened at all, saved instead through a combination of clever engineering and fortunate timing that could easily have gone the opposite direction. This spacecraft originally launched with an entirely different assignment. Its job involved travelling to a completely different asteroid, carefully approaching its surface, collecting a physical sample of rock and dust, and successfully returning that precious sample safely back to Earth. That original mission succeeded brilliantly, delivering scientists genuine physical material from an ancient asteroid for detailed laboratory study, a remarkable achievement in its own right. Once that primary mission wrapped up successfully, mission planners faced an important decision. The spacecraft itself remained fully functional, still carrying working instruments, still capable of travelling further and gathering more data. Retiring a capable spacecraft simply because its original assignment finished would have wasted enormous remaining potential, built at tremendous cost and effort. Instead, engineers calculated a bold alternative path: redirect the spacecraft entirely, sending it on an extended journey toward Apophis, timing its arrival to align precisely with the historic 2029 flyby. This required recalculating an entirely new trajectory, adjusting the spacecraft's remaining fuel budget, and ensuring every system originally designed for one specific mission could adapt successfully to a completely different scientific target. This kind of mission extension carries genuine risk. Spacecraft systems designed and tested for one specific set of tasks do not always translate perfectly to new, unplanned objectives. Every instrument, every navigation system, every communication protocol needed careful re-evaluation to confirm it could reliably support this new assignment, potentially years beyond what the original mission timeline ever anticipated. The payoff for taking this risk proved enormous. Rather than requiring an entirely new mission, built from scratch, launched specifically to study Apophis, scientists instead secured a capable, already proven spacecraft, positioned precisely where needed, at a fraction of what building a dedicated new mission would have cost. Extending an existing mission this way represents one of the more elegant examples of resourceful engineering in recent planetary science history. Today, that spacecraft carries a new name reflecting its new purpose and a new destiny intertwined directly with Apophis itself. Its presence during the historic 2029 flyby means humanity will not simply watch this transformation unfold from a comfortable distance using ground-based telescopes alone. A dedicated spacecraft, riding directly alongside the asteroid, will capture the moment up close, converting what could have been a purely observational event into an active front-row scientific investigation unfolding in real time. Long before any spacecraft or radar dish confirms exactly what happens to Apophis during its historic flyby, one older, simpler technique will already be gathering critical clues. Scientists call it a light curve, and it works by measuring nothing more complicated than how bright an asteroid appears over time, watched carefully as it tumbles and rotates through space. Here is the basic principle. As an irregularly shaped object like Apophis tumbles, different portions of its surface face Earth at different moments. A wider, flatter side reflects more sunlight back toward observing telescopes, appearing brighter. A narrower, thinner side reflects less, appearing dimmer. Track this brightening and dimming pattern carefully over time, and scientists can reconstruct surprisingly detailed information about an object's shape and rotation without ever needing to send a single spacecraft close enough to see it directly. Before its historic encounter with Earth, Apophis already displayed an unusually complicated light curve, one that never quite settled into a clean, repeating pattern. That irregularity reflects its tumbling rotation state discussed earlier, wobbling around an unstable axis rather than spinning cleanly like a well-thrown football. Reading that irregular pattern accurately requires considerably more sophisticated analysis than tracking a normal, steadily spinning asteroid. Following the 2029 flyby, scientists plan to immediately resume this same light curve tracking, searching specifically for changes compared to earlier measurements. A shift in rotation speed would show up as a change in how quickly the brightness pattern repeats itself. A shift in the spin axis orientation would alter which portions of the surface face Earth at different points during each rotation, subtly reshaping the entire brightness pattern. This technique offers something genuinely valuable, an independent method for verifying whatever changes more complex physical models predicted in advance. If detailed simulations suggested Apophis's rotation period should drop from 30 hours down toward 10 or 15 hours, light curve measurements taken after the flyby can directly confirm whether that prediction actually held true without requiring any additional spacecraft observations. Combining this simple ground-based technique alongside far more sophisticated radar tracking and spacecraft imagery creates multiple independent lines of evidence, each one checking and confirming the others. Science grows considerably stronger when several completely different methods arrive at matching conclusions, rather than relying on any single measurement technique alone. For an object that has already surprised scientists more than once throughout its documented history, first with its startling 2004 impact odds, later with its complicated tumbling rotation, this kind of layered, redundant verification carries real importance. Every additional confirming measurement builds greater confidence in exactly how much Apophis changed, transforming a series of educated predictions into a genuinely, thoroughly verified scientific record. Scientists rarely get to run true experiments on planetary scales. Chemistry happens in beakers, physics happens in particle accelerators. Testing how gravity reshapes an asteroid, however, has always remained purely theoretical, built entirely from mathematical models and computer simulations, because no one could ethically or practically arrange for a real asteroid to fly dangerously close to a real planet just to observe what happened. Apophis changes that equation entirely, delivering exactly this kind of real-world natural experiment without anyone needing to arrange it deliberately. The asteroid's own orbit, shaped by billions of years of gravitational interactions across the solar system, happens to bring it close enough to Earth in 2029 to create genuinely testable, measurable conditions, all without any actual danger of collision. Researchers describe this specific type of event as offering a unique opportunity to directly observe how Earth-crossing objects interact with our planet's gravity field, describing it as a natural experiment that could meaningfully improve our broader understanding of potentially hazardous objects. That phrase, natural experiment, captures something important. This is real data, gathered from a real event, rather than purely theoretical modelling built on assumptions alone. The distinction matters enormously for planetary defence more broadly. Computer simulations, however sophisticated, always rest on certain assumptions about how rubble pile asteroids behave under gravitational stress. Real-world data either confirms those assumptions or reveals where they fall short, providing scientists with genuine ground truth against which every future model can be measured and improved. This becomes especially critical because humanity may someday need to actively deflect a genuinely dangerous asteroid, one on a real collision course with Earth. Any deflection strategy depends entirely on accurately predicting how a target asteroid will respond to applied force, whether that force comes from a spacecraft impact, a gravitational tractor, or some future technology not yet developed. Miscalculate that response and a deflection attempt could fail entirely, or even make a bad situation worse. Apophis offers a preview of exactly this kind of response, except triggered by gravity rather than a deliberate spacecraft impact. Scientists studying how the asteroid's spin, surface and orbit change during this flyby gain genuine insight into how rubble pile objects generally respond to strong gravitational forces, insight directly transferable to future planetary defense scenarios involving completely different asteroids. Few events in the history of space science offer this particular combination: genuine scientific rigor, zero actual risk to Earth, and direct practical relevance to protecting the planet from future threats. Apophis is not simply passing by to be observed from a comfortable distance. It is actively demonstrating, in real time, exactly the kind of physics humanity may one day depend on to save itself from a very different asteroid, arriving under very different, far more dangerous circumstances. Most public discussions about science search for clean, confident answers. Will this happen, or will it not? Scientists studying Apophis have taken a different, more honest approach throughout this entire story, openly acknowledging uncertainty rather than pretending to know more than the data currently supports. That honesty deserves genuine appreciation, especially given how dramatic and high stakes this particular story has become. Consider everything already explored across these chapters. The rotation period might drop to 10 hours, or it might land closer to 15. The Yarkovsky drift rate might fall to 160 meters per year, or climb toward 300. The spin axis might shift by exactly 10 degrees, or considerably more. Each of these predictions comes wrapped in a genuine range, rather than a single, falsely precise number. This range exists for good scientific reasons, not because researchers lack sufficient expertise or effort. Remember the missing piece explored earlier, the internal density and structure of Apophis, information that remains genuinely unmeasured until the flyby itself provides new data. Every prediction currently available represents the honest boundaries of what current knowledge allows, rather than a confident singular forecast. Scientists have grown increasingly comfortable communicating this kind of uncertainty publicly, recognizing that admitting the limits of current knowledge builds more genuine trust than projecting false confidence, only to be proven wrong later. This matters enormously given how badly the original 2004 impact scare damaged public trust temporarily, before more complete data finally resolve that uncertainty years later. The 2029 flyby offers something valuable specifically because it will finally convert this entire range of predictions into confirmed, measured reality. Instead of a spread of possible rotation periods, scientists will measure one specific actual number. Instead of a range of possible drift rates, they will observe one specific actual value. Uncertainty converts directly into knowledge, in real time, live, in front of instruments and spacecraft positioned specifically to capture that exact moment. This transformation from uncertainty into confirmed data represents one of the most valuable aspects of the entire encounter, arguably more valuable than any single individual measurement gathered along the way. Watching predictions succeed or fail in real time teaches scientists exactly where their current models excel, and exactly where those same models still fall short, informing every future asteroid study that follows. Apophis has spent over 2 decades teaching scientists lessons about honest, careful, evolving science, from the initial fear-driven headlines through the careful radar work that erased that fear, and now toward this final test, where every remaining uncertainty finally meets real, measured reality. The Chaos God has never simply delivered danger. It has consistently delivered lessons, each one arriving exactly when scientists needed it most. Understanding what Apophis actually represents requires separating 2 very different questions that often get confused in public conversation. What would happen if an object this size actually struck Earth? And separately, will Apophis itself ever actually do that? These 2 questions deserve entirely different, carefully distinct answers. Start with the first question, purely hypothetical at this point given everything already confirmed about Apophis's safe trajectory. An object measuring roughly 375 meters across, striking Earth at typical asteroid impact speeds, would release energy far beyond anything in modern human experience, comparable to thousands of the largest nuclear weapons ever tested, concentrated into a single violent moment. The immediate destruction would extend across an entire metropolitan region, potentially hundreds of kilometers, depending on the specific impact angle and location. This is precisely why the original 2004 discovery generated such intense concern among scientists. An impact of this scale would not threaten the entire planet's survival, the way an object several kilometers across might, but it would represent a genuinely catastrophic regional disaster, capable of devastating a major city and surrounding areas, with consequences rippling outward through global economic and humanitarian systems for years afterward. Now turn to the second question, the one actually relevant to real events unfolding in 2029. Every scrap of currently available data confirms Apophis poses no impact risk to Earth for at least the next century. Decades of careful radar tracking, repeated independent calculations, and continuously refined orbital models all point toward the same confirmed conclusion. The historic flyby happening this coming April represents a close approach, dramatic and scientifically significant but fundamentally safe. Holding both of these truths simultaneously, understanding the genuine destructive potential this size of object carries, while also confirming that potential will not become reality this time, represents exactly the kind of nuanced thinking good science requires. Fear without context leads to panic. Reassurance without context can breed dangerous complacency. The full, honest picture requires both pieces held together. This dual understanding also explains precisely why so much scientific effort continues pouring into studying this specific flyby so thoroughly. Apophis offers a genuinely rare opportunity to study an object capable of city-level destruction, up close, in complete safety, gathering data that could prove critical if a future object of similar size ever does find itself on a genuine collision course with Earth. Every measurement gathered during the 2029 encounter builds toward a single, practical goal: better understanding exactly how objects of this destructive potential behave, how they respond to gravity, and how planetary defense strategies might someday need to respond if a future Chaos God arrives under far less fortunate circumstances than this one. 7 hours might sound brief compared to the years of preparation leading up to this historic flyby, but within that window, an extraordinary amount of simultaneous activity will unfold across the entire planet. Coordinating this level of observation requires cooperation stretching across continents, institutions, and scientific disciplines rarely brought together this precisely for a single event. Picture the full scope of what happens during those critical hours. Radar facilities in California and West Virginia continuously bounce signals off the asteroid's surface, refining measurements in real time. Telescopes positioned across Australia, Africa, Europe, and Asia simultaneously track the same object crossing overhead, each contributing slightly different angles and perspectives. A dedicated spacecraft positioned nearby captures close-range imagery no ground-based instrument could ever achieve. None of this happens by accident. Coordinating instruments scattered across an entire planet, all aimed precisely at the same rapidly moving target, during the exact same narrow window, requires years of advanced planning, careful scheduling, and constant communication between research teams who may rarely interact under normal circumstances. Apophis has effectively united astronomers worldwide around a single, shared, unmissable scientific event. This kind of global coordination carries genuine urgency, because the flyby itself will not wait for anyone. Unlike a laboratory experiment that can pause and restart whenever convenient, this natural event unfolds on its own fixed timeline, driven purely by orbital mechanics established billions of years ago. Miss the window, and decades might pass before another comparable opportunity arrives. Time zones add another layer of complexity to this coordination effort. As Apophis crosses from the mid-Atlantic, over Africa, and into Western Asia during its ground track, different observing teams around the world experience completely different local times, some working through the middle of their night, others catching the event during evening hours, depending entirely on their geographic position relative to the asteroid's path. Despite these logistical challenges, scientists have spent years preparing precisely for this moment, building detailed observation schedules, testing equipment repeatedly, and establishing communication protocols designed to share data quickly across research teams during the flyby itself. Speed matters here, because early observations gathered during the actual encounter can help refine predictions and observation strategies for the remaining hours still unfolding. By the time Apophis finally departs Earth's immediate vicinity, curving back out into deeper space, an enormous volume of data will have been gathered, more comprehensive and detailed than almost any previous asteroid encounter in recorded scientific history. Turning that flood of information into confirmed published scientific understanding will take considerably longer than the 7-hour flyby itself, likely stretching across months or years of careful analysis. But the historic moment when all that data gets gathered arrives on a single, unmovable evening, watched by more instruments, more scientists and more curious observers than perhaps any asteroid encounter Earth has ever experienced. Somewhere between 7 and 8 billion people currently live on Earth. A meaningful fraction of that entire population, potentially numbering in the billions, will find themselves positioned somewhere within viewing range when Apophis crosses the night sky in 2029. Very few astronomical events in recorded human history have offered this scale of potential shared witness. Visibility maps developed by researchers studying the flyby suggest observers across Australia, southern and eastern Asia, Africa, Europe, and even portions of East and South America may catch a glimpse, weather and light pollution permitting. This represents an extraordinarily wide geographic spread for a single celestial event, stretching across multiple continents and vastly different time zones simultaneously. What exactly will observers actually see, though, deserves honest clarification. Apophis will not resemble a dramatic fireball, a bright flash, or anything closely resembling popular imagination of an asteroid encounter. Instead, it will appear as a steadily moving point of light, drifting smoothly across the darkness, brighter and considerably faster moving than typical background stars, but otherwise fairly understated in appearance to the casual observer. That understated visual reality contrasts sharply with everything happening invisibly behind the scenes. While casual observers see nothing more dramatic than a fast-moving dot of light, that same object experiences genuinely violent transformation, tidal stretching, surface shifting, and rotational changes, all completely invisible to the naked eye, detectable only through sophisticated scientific instruments working simultaneously alongside the public viewing experience. This gap between visual appearance and underlying reality captures something profound about the entire Apophis story. The most dramatic consequential events do not always look dramatic from the outside. A quiet point of light drifting silently overhead represents one of the most scientifically significant natural events humanity has documented in recent memory, its true significance hidden entirely beneath an unassuming visual surface. For the scientific community, this moment of mass public visibility offers a valuable secondary benefit beyond pure research value. Rare, accessible astronomical events like this one tend to spark genuine public curiosity about space science more broadly, drawing attention toward asteroid research, planetary defense, and space exploration that might otherwise remain confined purely to academic circles. Millions of people glancing upward on the same evening, watching the same object cross their sky, connected briefly by a shared moment despite being scattered across entirely different countries, cultures, and time zones, represent something genuinely rare in an increasingly divided world. A chaos god, once feared as a potential harbinger of disaster, instead becomes something closer to a unifying spectacle, watched collectively by more human eyes than perhaps any asteroid in recorded history. Every scar on the surface of Apophis tells a story stretching back billions of years, long before Earth ever developed complex life, long before continents settled into their current positions, long before humans existed to look up and wonder what drifted through the darkness above them. The 2029 flyby is about to add an entirely new chapter to that ancient story, one written not in millions of years, but in a single afternoon. Scientists studying rubble pile asteroids like Apophis believe these objects preserve genuinely primitive material, largely unchanged since the earliest days of solar system formation. Unlike Earth, which melted, differentiated into distinct layers, and continuously reshapes itself through volcanic activity, erosion, and plate tectonics, small rubble pile asteroids simply drift, largely frozen in whatever configuration they settled into shortly after formation. This preservation makes Apophis something close to a time capsule, carrying physical evidence about conditions present during the solar system's earliest, most chaotic period. Studying its composition, structure, and history offers scientists genuine insight into processes that shaped every planet, moon, and asteroid currently occupying our solar system, insight difficult or impossible to obtain through any other method. The 2029 encounter threatens to complicate this pristine record, at least partially. As tidal forces reshape the surface, as boulders shift position, as loose material resettles into new configurations, some of that ancient, undisturbed history becomes overwritten by fresh, newly exposed material. In a sense, Earth's gravity is about to partially erase pages from a book that took over 4 billion years to write. Scientists view this transformation with a mixture of genuine scientific excitement and careful documentation urgency. Before the flyby erases or alters certain surface features permanently, researchers are working to document Apophis's current state as thoroughly and precisely as possible, creating a detailed baseline record capturing exactly how the asteroid appeared immediately before its historic encounter with Earth. This baseline record becomes scientifically invaluable, regardless of what specifically changes during the flyby itself. Comparing detailed before and after imagery allows scientists to identify precisely which surface regions shifted, cracked, or resettled, effectively mapping the exact boundaries of Earth's gravitational influence across the asteroid's entire surface, boulder by boulder, region by region. In an unusual way, this partial erasure of ancient history creates entirely new scientific value of its own. Fresh, newly exposed material offers scientists a rare glimpse at subsurface composition never previously visible from Earth-based observations. The Chaos God may lose some of its oldest secrets during this encounter, but in exchange, it reveals brand new ones, buried just beneath the surface, waiting over 4 billion years for exactly this moment to finally come into view. Apophis represents a single object, but the lessons gathered from its historic flyby will ripple outward across the entire field of asteroid science, influencing how scientists study thousands of other objects scattered throughout our solar system, most of which will never come anywhere near this close to Earth for direct comparison. Consider how scientific knowledge typically advances in fields like this one. Researchers build models based on available data, then test those models against new observations whenever possible, refining and correcting them based on what actually happens compared to what was originally predicted. Apophis offers an unusually rich testing opportunity, one detailed enough to validate or challenge assumptions built into models applied across countless other rubble pile asteroids throughout the solar system. Every rubble pile asteroid shares certain fundamental physical properties: loosely bound material, weak internal gravity, and vulnerability to tidal forces during close planetary encounters. Whatever scientists learn about exactly how Apophis responds to Earth's gravity during this specific flyby provides a template, a reference point, that researchers can apply, with appropriate adjustments, toward understanding how other similar objects might behave under comparable circumstances. This matters enormously for planetary defense efforts extending far beyond Apophis itself. Thousands of near-Earth asteroids currently sit catalogued in scientific databases, most too small or too distant to threaten Earth directly, but a meaningful fraction large enough to cause serious regional damage should their orbits ever shift into a genuine collision course. Understanding how these objects generally respond to gravitational stress, informed directly by Apophis, helps scientists prepare more effective response strategies for whichever object eventually poses a real, confirmed threat. The timing here carries particular significance. Detection technology continues improving steadily, identifying increasing numbers of previously unknown near-Earth asteroids every single year. As that catalogue grows larger, the statistical likelihood of eventually discovering a genuinely dangerous object, one requiring an actual deflection response, continues climbing as well. Having accurate, real-world validated models ready before that moment arrives could prove critical to responding effectively under genuine time pressure. Apophis essentially serves as a dress rehearsal, conducted under completely safe conditions, for scenarios that could someday become genuinely urgent. Every measurement, every confirmed prediction, and every unexpected surprise gathered during this historic flyby builds directly toward better preparedness for whatever comes next, whichever future asteroid eventually demands humanity's full attention and response. This ripple effect, extending from one specific object outward across an entire field of scientific study, represents perhaps the most enduring legacy of the entire Apophis story. The Chaos God's brush with Earth in 2029 will not simply answer questions about one asteroid alone, it will help answer questions about every rubble pile object drifting through our solar system, quietly shaping how humanity prepares for threats that have not yet been discovered. Every remarkable scientific achievement described across this entire story traces back to a single moment of genuine fear, back in December of 2004, when astronomers first calculated a real, credible chance that Apophis might strike Earth. That fear, uncomfortable and unwelcome as it felt at the time, ultimately built the entire monitoring infrastructure now capable of tracking this historic flyby with such extraordinary precision. Before Apophis, asteroid monitoring existed, but arguably lacked the same urgency, funding, and public attention it commands today. The 2004 scare changed that trajectory permanently, demonstrating clearly and dramatically that near-Earth asteroids deserved serious, sustained scientific attention, rather than occasional, underfunded observation. Radar facilities like Goldstone and Green Bank, telescopes coordinated across entire continents, spacecraft missions redesigned specifically to intercept close-approaching asteroids. All of this infrastructure exists today partly because Apophis first taught scientists and funding agencies exactly what genuine stakes looked like. Fear, properly channeled, built the very system now capable of confidently predicting, tracking, and studying this historic 2029 flyby in extraordinary detail. This transformation from fear into capability represents one of the most valuable, underappreciated aspects of the entire Apophis story. A genuine scare, one that dominated headlines and worried scientists for roughly 2 years, ultimately produced lasting, tangible improvements to how humanity monitors and understands potential threats from space, benefits extending far beyond Apophis itself toward every asteroid discovered since. Consider how differently this story could have unfolded without that initial period of genuine concern. Would the same level of coordinated radar tracking exist today? Would spacecraft missions have been redesigned specifically to intercept close-approaching asteroids? Would this level of public and scientific attention currently surround the 2029 flyby at all? The fear itself, uncomfortable as it felt in the moment, appears to have been a necessary catalyst for everything that followed. This pattern extends beyond Apophis specifically, reflecting something broader about how humanity often responds to genuine, credible threats. Discomfort and concern, properly directed, frequently produce lasting improvements in preparedness and understanding, improvements that persist long after the original source of concern gets fully resolved or explained away. Apophis no longer threatens Earth. That threat disappeared years ago, confirmed through extensive, careful research. But the infrastructure, expertise, and heightened attention built specifically in response to that original scare remains fully active today, now redirected towards studying this historic flyby as a scientific opportunity rather than a survival threat. The chaos god that once frightened an entire planet ultimately taught that same planet how to watch the sky more carefully than ever before. Somewhere right now, teams of scientists are refining calculations, testing instruments, and finalising observation schedules, all counting down toward a single, unmovable evening in April of 2029. Unlike most scientific deadlines, which can shift, adjust, or extend when circumstances demand, this particular countdown operates on a timeline nobody controls. Orbital mechanics, established billions of years ago, dictate exactly when Apophis arrives, down to the precise minute. This immovable deadline creates a unique kind of pressure throughout the scientific community. Every telescope calibration, every radar system upgrade, every spacecraft trajectory adjustment must be completed and verified well before the flyby actually begins. There is no opportunity to pause, reschedule, or request additional preparation time once the historic evening finally arrives. Mission planners working on the accompanying spacecraft face particularly demanding preparation requirements. Positioning a functioning spacecraft precisely where needed, at exactly the right moment, to observe an unpredictably tumbling asteroid passing at extraordinary speed requires years of careful trajectory planning, extensive testing, and contingency preparation for scenarios that might unfold differently than current models predict. Ground-based observation teams face their own version of this same pressure, coordinating telescopes and radar facilities scattered across multiple continents, ensuring reliable communication between research teams working in vastly different time zones, and preparing contingency plans should weather, technical malfunctions, or unexpected complications interfere with observations at any single location. All of this demands extensive advanced coordination that cannot simply be improvised once the flyby actually begins. Beyond the purely technical preparation, public communication efforts have also intensified as the historic date approaches. Scientists and outreach organizations continue working to ensure accurate, clear information reaches the public, helping people understand exactly what will happen, why it matters scientifically, and importantly, why there remains absolutely no cause for concern regarding any collision risk during this particular encounter. This combination of technical urgency and public communication responsibility reflects lessons learned directly from the original 2004 scare. Scientists today understand, perhaps better than ever before, how quickly incomplete information can spread and create unnecessary public alarm. Clear communication, delivered well in advance of the actual event, helps ensure the historic 2029 flyby gets remembered as a celebrated scientific achievement, rather than a repeat of earlier confusion and fear. As the countdown continues ticking steadily toward April of 2029, anticipation continues building steadily across the global scientific community. Years of careful preparation, extensive coordination, and painstaking calculation are all converging toward a single evening, one that promises to deliver more concentrated scientific insight about asteroid behavior than perhaps any comparable event in recorded history. The countdown clock keeps running, indifferent to deadlines, funding cycles, or human schedules, counting down steadily toward a moment billions of years in the making. Despite decades of careful research, extensive radar tracking, and increasingly sophisticated computer modelling, one fundamental question about Apophis remains genuinely, honestly unanswered until the historic flyby actually happens. Exactly how much will this ancient chaos god change during its brush with Earth? Every model, every simulation, every careful calculation currently available offers only educated predictions, ranges of possibility rather than confirmed certainty. This lingering uncertainty is not a failure of modern science. It reflects the genuine complexity of predicting how a loosely bound, tumbling rubble pile object responds to powerful, invisible tidal forces during a close planetary encounter, a scenario humanity has never before had the opportunity to observe directly with this level of detail on an object this size and significance. Every chapter across this entire story is built toward this single moment of genuine scientific suspense, the rotation period potentially dropping toward 10 hours or possibly settling closer to 15, the spin axis shifting by 10 degrees or considerably more, the Yarkovsky drift rate falling toward 160 meters per year or climbing toward 300. Every one of these predictions currently exists as a genuine range, waiting for real, measured data to finally resolve which specific outcome actually occurred. Scientists have spent over 2 decades preparing for this specific moment, building the radar infrastructure, redesigning spacecraft missions, and coordinating global observation networks, all in pursuit of finally answering this exact question with genuine confidence. Every piece of preparation described across this entire story exists specifically to ensure that when Apophis finally makes its historic approach, nothing gets missed, nothing goes unrecorded, and no critical measurement slips through unobserved. The stakes extend well beyond simple curiosity about one specific asteroid. Remember everything already explored about planetary defense implications, about the broader scientific value extending toward thousands of other rubble pile objects throughout the solar system, about the practical lessons this encounter offers for humanity's future ability to respond to genuinely dangerous asteroids. The answer waiting to be revealed during this flyby carries weight extending far beyond Apophis alone. For over 20 years, this object has consistently surprised the scientific community, first with its startling impact odds, then with its unusually complicated tumbling rotation, then with the lingering uncertainty surrounding its distant future orbit. Nothing about Apophis's documented history suggests this next chapter will unfold predictably or without surprises of its own. As April of 2029 finally arrives, every instrument, every spacecraft, and every scientist involved in this historic effort will be watching for the same singular outcome, the moment when years of careful prediction finally meets confirmed, measured reality. Whatever specific numbers emerge from that historic evening, one truth already stands confirmed beyond any doubt. Apophis will not leave this encounter unchanged. Exactly how much it changes remains the one question still genuinely, honestly waiting for its answer. Step back far enough, and the entire story of Apophis becomes something larger than a single asteroid's brush with Earth. It becomes a story about transformation itself, about how even the most ancient, seemingly permanent objects in our solar system remain capable of sudden dramatic change when the right forces finally align. Consider everything this single object has already survived across its documented history. Discovery and obscurity followed by sudden global fear. Genuine, credible impact odds, followed by careful, patient research that erased that fear entirely. Decades of quiet monitoring followed by mounting anticipation as its historic flyby finally approaches. Through every stage of this journey, Apophis itself remained largely unchanged, tumbling steadily through space, indifferent to the fear, relief, and fascination it generated among the humans watching from below. That indifference is about to end. For the first time in this asteroid's entire documented history, and quite possibly for the first time in millions of years, Apophis is about to experience genuine, measurable, permanent physical transformation, triggered entirely by its brief encounter with Earth's gravity. The rotation that has remained steady for countless years may shift dramatically. The surface that has sat undisturbed since before human civilization existed may crack, shift, and resettle. The orbit that has followed a predictable path for decades may bend into a new, slightly different trajectory. This transformation happens without violence, without collision, without any dramatic explosion visible from Earth. It happens purely through gravity, an invisible, patient force reaching across tens of thousands of kilometers, working silently and effectively across a matter of hours rather than millions of years. There is something genuinely humbling about that fact. The most dramatic transformation in this asteroid's recent history will occur almost entirely invisibly, detectable only through careful scientific instruments rather than obvious visual spectacle. Every earlier chapter in this story has built toward understanding exactly why this transformation matters so deeply to scientists studying it. The tidal forces reshaping loose surface material, the spin changes revealing hidden clues about internal structure, the shifting Yarkovsky drift rewriting centuries of future orbital predictions. Each piece connects directly back to this same central truth. Apophis is about to become a fundamentally different object than the one first discovered back in 2004. And yet, despite everything changing, something essential about this story remains exactly the same. Humanity's curiosity, its determination to understand, predict, and prepare for whatever the universe presents. That drive remains as strong today as it was the moment astronomers first spotted this faint, unremarkable dot moving quietly against the stars over 2 decades ago. The rock changes. The sky above us keeps offering new mysteries. and our determination to understand both keeps growing stronger with every passing year. Every story eventually arrives at its final chapter, and this one belongs entirely to what happens after the historic evening finally passes. Apophis will complete its closest approach, curve back out into deep space, and continue drifting along its newly altered orbit, carrying forward every change gathered during those brief, transformative hours above Earth. The immediate aftermath will unfold gradually, not instantly. Scientists will spend months, likely years, carefully analysing the enormous volume of data gathered during the flyby itself, comparing predictions against actual measurements, refining models, and finally publishing detailed findings describing exactly how this ancient object responded to its encounter with Earth's gravity. The historic evening itself represents only the beginning of understanding what actually happened. What we already know for certain provides a solid foundation for everything still to come. Apophis will not strike Earth, not during this historic flyby, and not for at least the following century based on every currently available measurement. That fundamental safety has already been confirmed repeatedly through years of careful, independent verification. Whatever surprises emerge from the detailed data still to come, the basic safety of this encounter remains firmly established. Beyond that baseline safety, genuine transformation awaits confirmation. The tumbling rotation, potentially reset entirely. The spin axis shifted by degrees that would normally require millions of years to develop naturally. The surface reshaped by tidal forces powerful enough to dislodge boulders that had rested undisturbed since before human civilization began. The orbital drift, rewritten by changes to how sunlight interacts with a newly reshaped, newly reoriented object. This encounter will not be Apophis's last brush with Earth either. Remember, this same object continues crossing paths with our planet repeatedly across future decades, offering scientists an unusual, ongoing opportunity to study how this specific asteroid continues evolving over time, verified against real, accumulating observational data rather than pure theoretical prediction alone. The broader legacy extends well beyond this single object. Everything learned from studying Apophis during this historic encounter directly improves humanity's understanding of rubble pile asteroids generally, strengthening planetary defense strategies that could someday prove critical if a genuinely dangerous object ever does find itself on a real collision course with Earth. Fear, transformed patiently into knowledge, transformed again into preparedness, represents perhaps the most valuable outcome this entire story has to offer. An ancient chaos god, drifting quietly through space since before Earth's continents settled into their current positions, is about to meet the one force in the solar system capable of reshaping it in a matter of hours. When the encounter finally ends, Apophis will continue drifting outward, changed permanently, carrying forward a physical record of its brief, historic meeting with the planet it once threatened to destroy. Somewhere above our heads, a rock is about to prove that even the oldest, most ancient objects in our solar system are never truly finished changing.